In this video, we're going to look at the mathematical representation, specifically of large systems of equations, and in particular for the finite difference temperature models. All right, so when we started off with a fairly reasonable grid of our model for this plate, it had 5 by 5, so we ended up with 25 cells. That meant that we had a vector of unknown temperatures, T1 through T25, and that vector of unknown temperatures would have to be multiplied by an A matrix. Well, that A matrix has to be 25 by 25. And then it would equal our B vector, which would be 25 rows long. Now, let's acknowledge right off the bat, a 5 by 5 grid is not going to cut it. The assumption that the temperature does not change much on each cell is not going to be true because we're using pretty chunky, pretty big cells. So what if we wanted to use on our temperature block, so you're looking at our 20 degrees here and our 120 degrees here, if we wanted to cut this into 100 by 100, the last temperature would be, well, we have 100 in this row, 100 in this row, it would be T 10,000, 10 to the power 4, 100 squared. So that means that when we build our system of equations, we would have T1, T2, all the way down to T 10,000, which means our A matrix would be 10,000 by 10,000. We're talking big here. And then our B vector would be 10,000 long as well. So, looking at the 5 by 5 grid for our plate, turns into a 25 by 25 matrix and 25 long B vector. That's just at the edge of being doable by hand, but this larger one, 10,000 by 10,000, you're not doing that by hand. There's just no way that's possible, or certainly not in any way that can be easily checked or reproduced or tweaked. There's a whole host of reasons not to go down that road. Where it did make sense with the trusses to talk about manual creation, with the heat systems, it makes 0 sense. So we're going to have to find another strategy for that. So in upcoming videos, we're going to see how we can use loops in MATLAB to create those matrices. But just to get a sense for where we're headed, imagine that we're looking at this grid, and again, think of the temperatures. We have a cold center at the top, we have an insulated wall. So what we might expect is to see some sort of high temperature around this region, but it's also pretty warm along this barrier here. Then we expected to see it maybe colder, certainly colder in this corner, as it's bounded most closely by the 20 degrees in the insulated wall. And in the middle here, we might have some intermediate temperatures. That's a pretty reasonable thing to expect once we reach steady state with these kinds of environmental temperatures. Let's see if we can generate that kind of solution in MATLAB so we can visualize where we're heading before we get into the nitty-gritty. If we open the thermo file that's posted online, don't worry about the code, we're going to build that ourselves. For now, I just want to run this, and we're going to be using a 100 by 100 grid on this. Let's see what that looks like. There we go. Let's blow that up full size. What we can see is exactly what we laid out there, but in much finer detail. Temperature of 120 along this edge, we can see that. A little cooler along this edge, but we see a little hot wave in this corner. Middling temperatures this way, the cold blue along the bottom there, and a gradation along the insulated wall, basically from 20 smoothly up to that 100 degrees here. All of that internal calculation, perfectly balanced using the heat flow sum equals 0 to get this kind of high resolution picture of the temperatures in this metal plate. Again, a nice quantitative prediction using some of the well understood physics underneath it, and relatively little code to generate quite a complicated model for this equilibrium temperature distribution. It's good stuff. We'll see how to do this in upcoming videos.